All right, we're back and introducing the Fab Five Equations. We can use these 5 different equations that we're about to explain here in just a second for anything dealing with constant acceleration. So uniform acceleration, these 5 equations are fair game. Here are the 5 equations. If you notice, every single one of the 5 equations is missing one quantity. So the first equation is missing initial velocity. The second equation is missing time, final velocity, displacement, and acceleration. So keep that in mind. As long as you have all of these variables but one, and you leave out one of the variables, you can use these new equations. Again, these are all quantities and terms you've dealt with before. It's just now we have to look at what we're given, what we're missing, and what we're looking for, and choose what is the best equation for this situation. Again, to go over and review, A means acceleration, and we're going to use meters per second squared for the unit. VI is your initial velocity, and that's going to be in meters per second. Velocity final is going to be in meters per second as well. Time is always in seconds. And displacement, delta x, right, is just your change in position, and that's in units of meters. Don't forget that your velocity, your displacement, and your acceleration can all be positive or negative because they're vector quantities. Remember as well that this only can be used when there's constant acceleration. But for this class, in this case, we always are using constant acceleration, so it should be good. Ladies and gents, welcome to the Fab Five Equations. Here is a list similar to what you will be receiving. This list is a grid that can help you figure out which of the Fab Five equations to use. Say in a problem you end up getting information for velocity final. Oh, let me draw that in there, sorry. Velocity final. You're given a time and an acceleration. And the question asks you for displacement. Notice that you've been given 3 variables and you're looking for one of them. So the only thing that's left out is your velocity initial. You're not solving for it and you don't have any of that information. So on this chart, you'd look for the area that has an equation that doesn't use anything at all with velocity initial, which would be this one right here. NA means not applicable. Therefore, with that situation, you would use this first equation. Now, say in a problem you're given the time, you're given the displacement and the acceleration, and they're asking you, hey, what would the initial velocity be of this object? If you look at that, that means that velocity final has nothing to do with the problem. You're not solving for it and you're not giving it. So what equation would you use then? It's simple. You would use this one. Because there is no velocity final at all available in the equation, you are searching for velocity initial and you already have these 3 guys. So you've got the 4 check marks and the 1 not applicable that you're not interested in. So this equation would have been the best for it. Let's do one more example where they give you the initial and final velocity, and we've done that in a lab, and we've timed it, all right, and we want to know the acceleration of the object. So we have nothing to do with displacement, we know nothing about it, and it's not involved in the problem. So what equation would you use? Well, scroll down through your list until you get to, the area that says displacement has nothing to do with this problem. That means that we would use this equation. Velocity final equals velocity initial plus acceleration and time multiplied together. See, it's simple. When we use the grid, it makes sense and it's straightforward. All right, we won't do the entire problem, but we'll set it up, okay? So let's take a look at the information given. You have a time of 0 to 8 seconds. So you have t equals 8 seconds. That's given to us. We have an acceleration here of 2.0 meters per second squared. That's good. We have an initial velocity, right? V naught, that little circle on there really means initial velocity as well, just another way to write it. But it's a positive 6.0 meters per second. And we want to know, so forgive me, these are our givens. Our unknown that we want to know is displacement. So we want to know that. So if you take a look at your chart and your actual equations, let's take a look and see which one would work. Notice that the only thing not being used in this type of problem that isn't going to be solved for and isn't given to us is velocity final. So take a look and see which equation would not use velocity final. All right, if I look on my sheet where there's no velocity final whatsoever involved, I look at the equation on my sheet, it's the third one down, that is delta x, which we want to solve for, equals velocity initial, which we have, times time, which we are given as well, plus 1/2, that's easy, that's just 1/2, acceleration, excuse me, which is given to us as well, times time squared. Boom! We've got an equation that had nothing to do with velocity final. If I substitute that in, we can set up the problem, and then from there I'm sure you can do your algebra. You algebra studs you. It is still displacement because we're solving for it, so we leave that blank. Velocity initial is 6.0 seconds. Time is 8 seconds. Plus, ooh, I got a message, pardon me, 1/2. And then acceleration would be 2. And time would be 8, so 8 squared. Look at that beautiful equation. Now you have everything given to you, and all you have to do is solve for this sweet and sassy displacement problem. Boom, algebra prevails, constant acceleration. You got a great problem set up. What if we tried another problem? In this case, our givens are acceleration is 31 meters per second squared. We have an initial velocity of 0, right? Boom, meters per second. Sorry, this is our acceleration up here. We have a final velocity, it looks like, of 62 meters per second. Do we have any other information? Nope, but we do want to find displacement. So the question is, my unknown, my displacement. All right, so look at everything we have. We're dealing with looking at displacement. Velocity final, velocity initial, and acceleration are given. What is the one variable or quantity not involved at all in this type of problem? Well, the answer is what? Time. Absolutely. Time isn't involved at all, so I'm going to look on my sheet and say, okay, where's my frowny face on time? Where is time not applicable? And I found it. It's my second equation down on my sheet. Might be different on yours. But velocity final squared is equal to velocity initial squared plus 2 times acceleration delta x, which is displacement. All right, notice once again to reiterate, there's nothing to do with time in this equation. That makes sense because you're not solving for your time and you haven't been given time at all. So if we plug in this equation, I've got 62 squared equals 0 squared plus 2 times my acceleration, which was given to me, 31, times my displacement, which I don't know. Now I can solve for x, or delta x, using algebra, which, again, you're algebra ninjas, so you should have no problem with this. See, it's not so bad. It looks like a lot of different variables, but when you break it down by your givens, your unknowns, and you find the proper equation, all of a sudden, it's just a little bit of an algebra problem to fix, and you get the right answer in the end. Beautiful. All right, last one. Let's rock this out. Spacecraft is traveling at a velocity of 3,250 meters per second. Now, I have no idea if that's initial or final velocity, but I know it's a velocity, so I'll put it down and fix it later. The spacecraft starts to slow down. Okay, if we're slowing down, we're going to decelerate. That might be important to think about. So I better make sure I realize that this is a positive velocity in case I have to deal with acceleration. The acceleration's magnitude, meaning just the value, not the direction, is 10 meters per second squared. Now, if I'm slowing down and the velocity is in the positive direction, that must mean that acceleration is opposite, in the negative direction. All right? What is the speed of the spacecraft when the displacement of the craft is 215 kilometers? So my displacement ends up being in the positive direction, 215 kilometers, which, by the way, if this is kilometers, we should definitely convert that to meters. So just multiply by 1,000, right? So 215,000 meters. There you go. That's delicious. All right, relative to the point of the retro rockets beginning to fire. All right, so a lot going on. I've got a velocity, since it was going at 3,250 meters per second, and then it's going to slow down. I could assume that that's my initial velocity right here. I was given acceleration. I have displacement. The question is, what am I looking for? They want to know what is the speed of the spacecraft after it starts stopping. So that would be my final velocity that I'm looking for. All right, now am I ready to look at my Fab Five equations? Darn right. I've got velocities, acceleration, and displacement. So the only thing I don't have is time. So just like the previous question, since I didn't have time, time is not applicable at all. I'm not solving for it, not giving it. I'm going to use that same equation I used last time, which was VF squared equals VI squared plus 2 times acceleration times displacement. Do I want to plug it in? Yeah, I do. I'm excited about this. I have no idea what my final velocity is, but I do know my initial velocity, and that's going to be squared. I know my acceleration is -10, and my displacement is positive 215. Sorry, trying to squeeze it in there. I'm going to get some better pens so I can write this better. But now I got an equation set up. Don't forget, after you get VF squared by itself, you will have to take VF and square root both sides of the equation to end up getting velocity final by itself. All right, but there's a little intro, should get you going and get you some good ideas. Good luck. Set up the problems using the guess method if you can. That'll make it a lot easier to pick the proper equation for the Fab Five. Peace out, J Physics.